Okay, so here we're asked to predict the product and draw the mechanism of this reaction. Now, this is an electrophilic aromatic substitution reaction. More specifically, it's a Friedel-Crafts alkylation. So we know that because we have an alkyl halide here, in this case an alkyl chloride. And we also have as another reagent aluminum chloride, and that's going to be the catalyst for this reaction. So in order to actually predict the product, I think it's best to do that through drawing the mechanism. So let's start with that. The first thing we need to do is we need to create a strong electrophile, because we know that that benzene ring is not a very good nucleophile, so we need to give it something really electrophilic to attack. And so we're going to do that using the aluminum chloride catalyst. So what we'll do is have the alkyl chloride, specifically the chlorine atom, is going to attack the aluminum chloride. And so what we get from that is a complex that looks like this. The chlorine has a positive charge, aluminum has a negative charge. And now the really important step is we're going to break the bond between this carbon and the chlorine. So those electrons are going to move onto the chlorine. And here we're going to create a carbocation. So that carbon is going to end up with a positive charge. So we'll have our aluminum chloride reagent down there, and that's going to come back into play in a moment. But now we have this 4-carbon alkyl fragment, like that. And we have a carbon, the carbon at the end has a positive charge. So this is a primary carbocation, and we know that primary carbocations are pretty unstable. And so if possible, they'd like to rearrange into maybe a secondary or tertiary carbocation. In this case, we can do that. At least we can get to a secondary carbocation. So we can use this hydrogen atom right here. And essentially, we're going to move the positive charge over to the right 1 carbon. But the way we do that mechanistically is we take one of the hydrogens attached to this carbon that's going to be our secondary carbocation, and we move those electrons over to the carbon with the positive charge. And so this is a hydride shift. We're just going to move the hydrogen over onto the next carbon. So, excuse me. So what's that going to look like? Well, our new carbocation is going to look like that. And the hydrogen atom that we moved is just going to be right there on that carbon now. All right, so now we have a really strong and at least fairly stable electrophile. And so now we're going to bring the benzene ring back into the picture. So we'll have our benzene ring here. And now it's got a strong electrophile to react with. And so the pi bonds here that are in our benzene ring are going to come and attack the carbon with that positive charge. And now we're going to, this is going to break aromaticity, and so we're going to form an rhenium ion. Okay, so those 2 double bonds stay the same. We've got a hydrogen that's there, and in fact, that hydrogen was in the benzene ring to begin with. And now we formed a carbon-carbon bond between this carbon and what used to be our carbocation, but now it's just, make that look better, it's just an alkyl fragment with 4 carbons like that. And of course, we've got to remember our positive charge there on that carbon. Okay, so now our aluminum chloride is going to come back into play. There it is. All right, and now we need to reform aromaticity. And to do that, we're going to do an elimination reaction. So we're going to have these electrons here between the chlorine and the aluminum come and grab that hydrogen atom. And then at the same time, these electrons that are making the CH bond are going to come down here. That's going to satisfy that positive charge, and we're going to reform aromaticity. So what we get from that is we get our substituted benzene ring with the alkyl group on it. And as side products here, we're going to get HCl, hydrochloric acid or hydrogen chloride gas, which is going to come from this chloride grabbing the hydrogen atom there. And then we're going to have the remainder of that aluminum chloride, AlCl3, catalyst regenerated. And there we go. That's the mechanism for a Friedel-Crafts alkylation reaction.